Welcome back. In the last couple of lectures, we were discussing about the traffic management techniques. We'll continue that discussion on the traffic management today as well. So, I want to discuss a little more detail in these three things. We understood that traffic management is primarily done through these three techniques called policing, shaping, and scheduling. So, what I want to cover today is basically how exactly the policing, shaping, and scheduling work is done inside the router, and what are the algorithms or the mechanisms that are used for this shaping, policing, and the scheduling. Let's begin with the first method called as the traffic policing. Policing is required or to make the end user traffic adhere to some agreed upon traffic rate. So, whenever the transmission rate is violating the condition or the agreed upon transmission rate, then you need to take the policing actions. So, what I mean by that is, if you have a router, let me call this router as R1, and there is a user, let me call that user U1. He is transmitting the traffic to this router or to any other destination, and that is flowing through this router. And let's assume that the user has agreed to transmit at a peak rate of 1 Mbps, and if the user input or the traffic arrival rate at this router R1 exceed this U1, then you need to take the corrective action. That corrective action is called as the policing. So, you observe the rate of the arrival or any other parameter that you agreed upon, and then you take the corrective actions for the violations. So, the what is the action, corrective action? So, this is, we understood that there are primarily two things that the policing action can do. One is, if the arrival is exceeding the agreed upon rate, then you need to, the simple thing that you can do is to drop the packet. Up to 1 Mbps you are supposed to transmit, you admit and pass on to the next link. If it exceeds that, then you drop the packet right here. So, that is one thing. And the second thing is, if there is a capacity available, remember this is the shared link, it has got a capacity C. If no other user is presently utilizing that capacity, if the spare capacity is available, and although at this router R1 the arrival rate of the user U1 is exceeding the agreed the rate, then since the spare capacity is available, you can do the transmission. You do the transmission with the condition that you mark the packet. What I mean by that is, so the packet is arriving at this router, let me call that packet as P, and it has got two things. One is the header portion, second one is the payload, and the router is here and the packet is arriving router and is exiting, and you mark this packet. Marking by that mean you set the differentiated service field inside the IP header. It has got bunch of headers, be it the link layer header, the IP header, and the TCP header, and the maybe the application layer header itself. You pick up the IP header from this packet and set the differentiated service field and send it. So, how does this help? Although the link between R1 and R2 probably is underutilized, you are able to transmit in excess of 1 Mbps, but R2 to some other, the next stop router R3, the capacity may not be available. So, it is an indication for the downstream routers to drop the packet if the capacity is not available. So, if it has to make a choice for dropping certain number of the packets, then probably the packets exceeding the 1 Mbps capacity are the candidates for dropping. That is the meaning of that. So, that is how the policing action is done, primarily to take the corrective action. Corrective action is, here is the drop or mark. When you are receiving the packet, when receiving means the router R1 is receiving the packets from the user U1. So, when the one router is sending a packet to the second router, there might be an agreed upon rate at which the router R1 is supposed to send it to the R2. Although on an individual router we may not do it, but on an aggregated level, one network sending the traffic to the another network, there might be some contract at peak rate at which the first network is supposed to transmit to the second network. Then you actually do the shaping. So, in order to enforce the constraint that I will not be transmitting more than what is agreed upon, you do the shaping. So, what are the things that you do inside the shaping? You basically delay the transmission and you put the packet inside a queue which has got a finite buffer, and you make it wait and then you transmit. These are the two things that happens inside the router. So, these two things, be it the policing or the shaping, are governed by something called as SLAs, which we discussed earlier as well. So, SLAs are the which packets, how much, when to mark, what to mark, when to drop, when to delete. Those decisions are governed by these SLAs. So, the actions for the policing is basically you either decide to transmit the packet. So, when you transmit it, when the arrival rate from the user 1 is less than the agreed upon condition or the agreed rate, and you decide to drop the packet when it is in excess and you do not have the capacity to accommodate the excess capacity, that time you drop it. So, if there is a spare capacity available at the outgoing link, and the in spite of user transmitting the traffic in excess of the agreed upon rate, then you mark the packet and send it to the next stop. And these things, whether to drop, mark, and who is transmitting, the choice of determining what action to apply for the particular series of the packets is done through the classifier, which we studied earlier. And classifier has got a collection of the rules, and it might happen that more than one rule need to be evaluated against a particular packet. So, you go one rule at a time, and then subsequently you go and evaluate if any other rule is actually applicable. So, all of this, whether you decide to mark it, transmit it, drop it, or do this, you need to go through a series of rules inside your classifier to arrive at a particular the choice. And it is possible that many different the rate transmission rates are possible. So, even for a particular user itself, you might say that I am going to give this peak rate if this is the condition, if this peak rate, if this is the condition, something like that can be defined. So, as long as the SLAs are very clear what to happen, when it should happen, then it is actually quite very clear. So, different but the policing itself can be done with or a bunch of users transmitting to this router. So, they are separated, or is a different set of the rules are defined for them, the user 1, user 2, and you can apply those rules to the router. So, user 1's traffic is going at a certain rate, user 2 is traffic is going at a different rate, that is possible. So, this policing action, as I said, although we saw the picture of user transmitting the traffic to the first stop router, usually the first stop router is the one which actually does this policing action, but the notion of the first stop router can be different. So, one action is where the end user is transmitting to the router, and this router R1 has got an outgoing link. There you are doing the policing action. This is the router where you are doing the policing action. Or it might also happen that the end user is somewhere here and his traffic is going to the first hop network, and this network has got internally a series of router, and the traffic passes through these routers. The policing action is happening here, and then when it is exiting one network and entering into the second network, so, from this border router to the border router of the second network, this is the network number 1, and let me call this network as network number 2. And again you do a marking, you do whatever the rules you want to apply right here, which is an edge router, and you come to you in between this and this one, nothing actually happening. These routers which are internal to the this network 1 are basically primarily looking into that marking which is already done and then just transmitting the packet to the next hop router. So, when the packet arrives at the border router, when it is transmitting at the next hop router, this router is receiving the packets from the border router of a previous network. There also the policing action can be done. So, here at this point of time and at this location, so the policing action is happening. So, when I say that incoming traffic is actually policed, so if the network 1 violates the transmission rate, agreed transmission rate, then the network 2 can decide to do the policing action. Basically, it can drop, okay, network 1, you were supposed to transmit at so and so rate and you are exceeding that rate, I am going to take the corrective action. So, at every, let us say the network 1 we can think of as an autonomous system, network 2 as a different autonomous system, and the source and destinations are apart or separated by 10 different autonomous system. At 10 different places the policing action is happening during the transmission. So, here is a picture which is actually showing in the network where exactly the policing and sweeping actions are taking place. So, as I said, every time a router receives the packet or receives the traffic from either the end user or the network, there the policing action is required, and every time a router is sending a traffic to some other network, that time shaping is required. So, what you see on this diagram is a bunch of computers connected to this router. Let me call this router as R1, and a bunch of computers connected to, on the right hand side to this router. Let me call this router as R2. And any computer on the left hand side transmitting the packet to some computers on the right hand side is going through this router R1. So, the packets of, let me call this computer C1, C1's traffic is arriving at the router R1. Now, R1 is the place where the policing action is happening. So, if C1 is supposed to send at a particular rate, let us say 1 Mbps, any excess traffic of in excess of 1 Mbps will be dropped or marked at the R1, and anything that is going to the C1 received from the other end would be saved at the R1. So, traffic exiting the C1 and going to R1 is policed, and traffic exiting the R1 and received at C1 is saved. That is the best way to understand what is saved and what is policed. And again you can see that this traffic, assuming R1 is part of the same autonomous system as these routers, and R2 is part of the this autonomous system number 2 as that of these bunch of the routers. So, across these routers whatever is marked in the yellow color, so no policing and shaping is happening. So, when the traffic is actually exiting the network, the shaping and going to the second autonomous system, shaping is happening, and whatever is received from the autonomous system 2 is actually policed at this router. So, that is how between the autonomous systems or the networks you do the policing and shaping operation. So, that is the big picture, and these are the two things, policing and the shaping are the two things of the traffic management action. So, the third one is the scheduling. So, here is another picture. If you can recollect the our previous lecture discussion, what we said is any router in the network has got a line card and it has got a switch fabric, and switch fabric is here, and the line card whatever is the packets are coming, they are arriving at a line card, and they are on a particular port. Let me call this port number as 1, 2, 3 and 4, and any packet which is arriving at an input port, now the header information of that packet is consulted, and then you look into the FIB information available at the input line card, and you decide on which output port number that particular packet should go through, and you request the switch fabric, I want to transmit this particular packet to so and so output port number, can you establish a link between this input port and that output port, and the switch fabric will come and do that link establishment. And the actions that we want to take, that is the routing decision or the forwarding decision that you are doing. In addition to that, we are doing the traffic management, and the actions of the traffic management are also done at the input port and also at the output port. So, what this picture is showing is what actions are done, what kind of the traffic management components are sitting at the input line card, and what kind of the operations are done at the output port. So, you can see that here is the notation: P stands for policing, B stands for buffer management, and S stands for scheduling, and R stands for shaping. Buffer management, policing, and the shaping scheduling happens at the input port, and the buffer management, scheduling, and shaping happens at the output port. So, policing, buffer management, scheduling happens at the input port, I repeat, and on the output port you have the buffer management, scheduling, and the shaping actions happening. Remember, there are two queues. One is called as the input queue, where the arriving packets are put. This is at the input line card or the input port number, and once the FIB consultation is done and you decide on which port number you want to forward this packet to. So, there is a queue at the output port as well, and the packet comes and sits inside this output port. Now, you can decide in what order you want to pick up the packets from the output queue itself. So, let us say there are some series of packets which have arrived on the input port number 1, there are some other packets which have arrived on the input port number 2, and all of them want to go to the exit, take the exit route of port number 3, and the next stop whatever is connected to the port number 3, and then you have a mixture of the packets coming from the port number 1 and another set of the series of packets coming from the port number 2. They are all sitting inside the queue that is available at the output port number 3. And now maybe the P1 is from the which has come from the port number 1, P2 has come from the port number 2, again P3 has come from port number 2, and P4 has come from the port number 1. Now you can decide, so whether I want to give transmit the packets arrived on the port number input port number 2 with a priority or not. That is why this scheduling operation is required. So, in a nutshell, policing, buffer management, and scheduling happen at the input port, and the buffering, scheduling, and the shaping operations happen at the output port when you want to transmit the packets on the output line. Okay. Now, the question is, how do exactly you do the both policing and shaping? So, policing we want to do, we said that anything in excess of the agreed upon rate would be either dropped or marked, and in while shaping you might put them inside the buffer and delay the transmission. Now, the question is how exactly this is done. How do I determine at what rate the end user is transmitting? So, if at all is transmitting at more than certain rate, what exactly you want to do? So, in practice this is done, both shaping and policing are done with an algorithm called as the leaky bucket algorithm. So, the conceptual idea is the following: you can assume that there is a bucket which has got a finite capacity, and the packets which are arriving from on the input line card are put inside this bucket, and this bucket has got a hole at the bottom, and the hole is of the fixed size, and the packets are exiting from that hole at a constant rate. So, that is how you bring the notion of the one rate. So, let us visualize how the leaky bucket algorithm would work. Here is the bucket, and the packets are coming to this bucket at a certain rate, and this might be, let us say this user U1 is transmitting to this router, and the bucket is available at the router, and so user is U1 is supposed to transmit at 1 Mbps rate, and if he is transmitting at more than 1 Mbps rate, those packets are buffered inside this bucket. So maybe the packet P1, P2, P3 are put, all of them are put inside this bucket, and they take turn. So depending upon the size of the hole available at the bucket, they are exiting at a constant rate. So such an algorithm is called the leaky bucket algorithm. So the bucket leaks at a constant rate. This algorithm was primarily designed for keeping the ATM networks in mind. So ATM networks has got the packets, whatever we are calling it as, they are in technically in the ATM networks are called as the cells. Cells arrive at a certain rate, and they are put inside this bucket, and the cells are exiting from this bucket at a constant rate. So and one of the nice thing about the ATM network, the cells, is all the cells are of the equal size. So unlike the IP packet can carry variable amount of the data inside it, but the ATM network, the cell has got a fixed size content inside, and so every time something exits the network, a fixed cell size cell is exiting the bucket. So we call that exiting is called as the bucket leaks at a certain rate. So that we call it as the peak cell rate. When the bucket is full, something is given by the end user, so that is exiting at this particular peak rate. If something is not available, then it is not nothing is actually flowing through this bucket. So in a way, the bucket itself has got a finite capacity, and the capacity can vary. So it can accommodate maybe 10 cells, 100 cells, 1000 cells. So that controls the bucket size, dictates the term something called as the tolerance level. So this tolerance level is something to do with the end-to-end delay. So let us say the source is and destination are 10 hops away, and at every router in between you are having such a buffer bucket, and the packets are actually, here is your destination, here is your source, and the cells are now put inside this bucket at every router. Now every router the has got this bucket has got a capacity, and larger the capacity that you have, larger the number of the cells that gets accumulated inside the router or this bucket when the transmission rate is exceeding the available capacity. So what it means is, more the capacity you have, more the number of cells getting accumulated, more the time it takes for them to exit the bucket. So thereby the end to end delay, I transmit, the source is transmitting a particular cell and it is expecting it to be delivered at a certain time, and if the, by virtue of putting more capacity, more size buffers, more size bucket inside the routers, what we made is the cells to wait in each of these router for a longer duration of the time. If the source is constantly pumping the packets, these cells will spend more time inside these routers, inside the buckets, then I may not be able to meet the end to end delay that upon. So that is why it's a little counterintuitive. The larger the capacity of the bucket, the larger the time they spend, and then larger the end to end delay. So that we may not be able to afford. So in a nutshell, what I want to achieve, what is the end to end delay I want to bring in, and how much is the buffer capacity that I want to include inside this leaky bucket is the question. I can actually adjust that accordingly. So as I said, arrival of the packets, they are putting inside, they are put inside this bucket and then they are exiting. So once the bucket is full, then the packets are lost or the cells are lost. When the, if let's say the 1000 cells you can accommodate inside this buffer, and when 1000 cells are sitting inside this bucket, the 1001 cell that is coming would be automatically dropped. So I can bring some kind of the differentiation while dropping, whether the newly arriving packets are dropped or something else which is already sitting inside the bucket itself is removed and then made room for the newly arrived packet. That is the question. So that is the something to do with the scheduling operation. So that differentiation you can assign a notion of the priority while deciding which packet to drop from the bucket. So every time something comes inside the bucket, there is a counter kept. That counter increments, that will indicate how many cells are actually buffered, and every time a cell exits from the bucket from the bottom, there is the counter is actually decremented. So if let us say the counter can go up to 1000. So if the counter ceiling value is 1000 and the minimum value is 0. So when one cell exits, you may decrement it by 999, and then a new packet can come and sit inside the bucket. So that's how the leaky bucket algorithm actually works. So remember, this is actually working, operating in the ATM network. Cells have got a fixed sized capacity, and every packet is of the same size. So the notion of the number capacity defined in terms of the number of the cells is actually going to work. But when you use the IP network, this is not the case. So here is a picture which is actually showing how exactly the leaky bucket algorithm works in the ATM networks. So the cells are arriving on the left hand side. Here what is shown as packets is technically the cells, and there is a queue here, and this is where the buffer is or the bucket is. So this bucket is now operating in the form of the FIFO queue, where it is transmitting the first cell that has come into the bucket is the first one that is exiting the bucket, and every time a cell arrives, you ask this question whether this bucket is full or is it has the capacity. If it can accommodate 1000 cells, are there 1000 cells already queued up, or you have less than 1000 cells? That is the simple question that you ask. If you have 1000 cells already queued up, then you discard the packet right here. If there is a capacity available, then you put it inside the queue. So once the you put the cells inside this queue, then you can do decision, subsequent processing, where to forward it and how many of them to forward it. All that decision can be subsequently taken. So that's how the leaky bucket algorithm in the ATM network works with the FIFO queue. So FIFO queue is a very simple queue, but that is not the only type of the queue might have. There are other type of the queues. We will come back and discuss that in subsequently. So that is the leaky bucket algorithm was with respect to the ATM networks, and the concept of the leaky bucket algorithm in the IP network takes a little bit change. So the companion version in the IP network is called as the token bucket. So the reason why this change was required is because of the variable sized packets inside the IP networks. So here is a picture, the incoming packet. Let me call this packet as P1, this packet as P2. P1 might have let us say 200 bytes of the data, and the P2 might have 100 bytes of the data. The size of the packets inside the IP network is variable. So it can have 0 bytes, or at the maximum it can have 65,535 bytes of the data. The size can actually vary between these two, between 0 to 65,535. So now how exactly I define the how at what rate I want to transmit, because now the counter on a packet number is not going to work out. I need to define something else. So the token bucket the way it works is, at a constant rate I want to transmit certain traffic at a certain rate, and I am going to generate something called as the token at per unit of time. So this has got a fixed size quantity. So let us say I am going to generate 100 bytes worth of tokens per unit of time per second. So that is the rate at which the tokens are generated and put inside the bucket, and these tokens are getting accumulated inside the bucket. I am not, remember, in the leaky bucket algorithm, the cells are getting accumulated inside the bucket, But in the token bucket, the tokens are the ones which is getting accumulated inside the bucket. So, at any point of time, there are certain token number of the tokens available inside the bucket, and the packets are arriving on the input link. So, you match what is the size of the incoming packet, you take that, and then how many bytes I need to transmit. If the tokens worth that capacity is available inside the bucket, and then you will be able to transmit the packet, this packet. Otherwise, you need to drop that particular right there. So, if in this case P1 has got carrying 200 bytes worth of the data. So, if the tokens worth 200 bytes are available in the bucket, then you will be able to transmit it. Otherwise, the packet P1 is actually dropped it, or you might put it inside a queue and wait till 200 byte worth of the tokens are getting accumulated inside the bucket. So, the one shown here, the arbiter is the one which is actually checking or comparing what is the size of the data that is arriving and how much bytes worth of the tokens are available inside the bucket. So, that is a change. Otherwise, the rate at which you want to transmit, since the tokens are arriving at a constant rate, you are actually guaranteeing that the exit rate is constant, conforming to the what is the token generation rate. So, if your arrival rate is smaller than the rate at which the tokens are getting generated, then none of the packets are actually technically queued up or dropped inside the network or the routers. So, that is how this algorithm works. So, the leaky bucket algorithm or the token bucket algorithm, this is used in both policing operation and also in the shaping operation. So, both policing, when you want to curtail or reduce the rate of the transmission, or you want to when you want to receive the traffic from some user, you do not want to receive the excess amount of traffic, then both time the leaky bucket algorithm can be used. That is precisely for policing and the shaping operations.